Welcome to the EPG Padashala, the lecture series in computer science for the postgraduate program. And this is the compiler design module paper. We are on module 38. Today in this module we will be talking about the code improving transformations. The objectives of this module are to understand the algorithms for global common subexpression, copy propagation, loop optimizations. Earlier we have already talked about how to perform common subexpression elimination, how to basically formulate the data flow equations for every basic block, for reaching definitions, for available expression computation, and for the live variable analysis. In continuation with that, we have not actually looked at the algorithm per se for global common subexpression elimination or copy propagation or constant folding. So, in this module we will talk about all those things, but all these modules require a concept called as definition use chain as well as use definition chains. So, these two information are basically one and the same only, but it is just representing in a different way where which will be definitely useful for the global common subexpression algorithm as well as the other loop optimization techniques also. So, the DU or UD, that is definition use as well as use definition use define chains, they are a convenient way to access or use reaching definition information. The definition use chain, that is the DU chains, what it basically does is, given a definition, what are all the possible consumers of the definition basically produced. That is, supposing I am defining a variable x, okay, which statements, that is which statements or which basic blocks will use this definition of x is what we are computing as definition use. That is, given a definition, who will basically use it. And then the use define chains is just the reverse. Given a use, what are all the possible producers of the definition consumed. So, supposing I am saying A is equal to B plus C, B and C are going to be used. Who produced B and C is what we are trying to find out. Okay. So, these two information are definitely required for computing the live variable analysis, which we have already seen, where we have a use of a basic block and you also have a definition of a basic block. In addition to that, these two concepts will be used subsequently in all the modules where we will talk about copy propagation and constant folding. This is from another textbook where I have R1 is equal to memory of R2 plus 0 and R2 is equal to R2 plus R1 and R3 is equal to R1 into R4. Now, look at these three are definitions of R1, R2 and R3. Now, as you can see, the statement, the third statement uses R1. Okay. So, the definition use of R1 is from 1, it is being used by 3 as well as by 4, by statement 4. So, statement 4 and 3 uses R1 which was defined in statement 1. So, that is why the DU chain of R1 consists of whatever is defined in 1 is basically used by 3, 4. Similarly, 4 also defines R1. So, R1 is equal to R1 plus 5 and this definition of 4 is basically used by the fifth statement which is R5 minus R1. Okay. So, fifth statement basically uses R1. So, again the DU chain of R1, if it starts at 4, I can say it is going to be used by 5. Now, similarly, if you look at the DU chain of R3, so R3 has R1 equal to R4, that is defined here, and this R3, if you look at this particular path, okay, this particular path, basically the 11th statement is going to be using R3. Okay. So, the definition chain of R3 which was defined in 3 is being used at 11. Alternately, I also define R3 here, okay, which is going to be used by this 11th definition, okay, the statement at 11. Now, the defined statement R3 is going to be used here also. Now, again I can also say R3 into 2. So, we can also say 6 basically uses R3. Okay. Then on to the UD chain of R1, use definition. Wherever R1 is used, who has basically defined it? Now, look at the 12th statement. 12th statement R3 is equal to R1 into 2. So, R1 is being used here, but this value of R1 is being defined by this R1, okay, is being defined at this particular R1. So, that is what we call it as a use definition chain of R1. Now, typically as a thumb rule, what we do is, supposing within a particular block, okay, within a particular block, if the same variable is defined and used, we normally do not consider for the DU chain. Okay. So, here R7 is equal to R3 into R2, which is actually used by R3. Sometimes we do not consider that also. So, this is what we say. So, use definition chain and definition use chains basically are saying that definition use chain, that is, supposing a variable is being used, who is the producer of that particular definition of the particular variable is what we call as a definition use chain. And use definition chain, supposing something is being used, who is the producer. So, definition use is going to be who is the consumer, use definition is going to be who is the producer of the particular variable. So, these two are also required for the subsequent computation. Now, the global common sub-expression elimination, we have already seen this in the context of what it does basically, rather how is it getting eliminated. Now, how do you actually go about as a step-by-step process to eliminate this is what we have to look at. Now, the available expression algorithm, which we have already seen in the previous module, computes and informs whether an expression is common at a particular point P. Now, after identifying this available expression, we need to get rid of this if it is going to be a common sub-expression. Okay. So, if it is available from multiple blocks, then we need to get rid of that as a common sub-expression. So, the available expression will tell you that whether it is going to be available from block B1 or B2 or B3, whatever it is. So, if it is available from multiple blocks, then I will have to look at it and treat that as a common sub-expression. Now, the algorithm here is the input will be a flow graph with available expression information. The output will be a revised flow graph which is going to get rid of the common sub-expression across basic blocks. Now, the method is for every statement S of the form x is equal to y plus z, if y plus z is available at the beginning of S, we have to do the following steps. So, you look at statement by statement and then try to consider it. So, search backward from the statement S, the expression y plus z, create a new variable u, replace each statement w is equal to y plus z found in the first step by u is equal to y plus z and w is equal to u. That is where you could encounter a statement of this particular form, you are simply saying using a new variable, you are assigning this value here and then the remaining will be simply a copy statement. Okay. So, replace statement S also by x is equal to u because now u corresponds to y plus z. So, this is done across all basic blocks till a value of change is observed either for y or for z. Now, that is done by the available expression algorithm that basically looks at it. Now, the searching for y plus z can be done as a data flow analysis problem. This is what we have already talked about in the previous module, where the available expression algorithm can be used where you can say its expression generated as an expression killed, and you would also had a in of every block computed as an intersection, and out of a block is also computed as a data flow equation, and this results need not be optimized. So, and this global common sub-expression elimination results in copy statement. For example, this case is not handled by the algorithm we have just now mentioned, where consider this scenario where a is equal to x plus y, b is equal to a into z. Okay. Now, c is equal to x plus y and d is equal to c into z. Obviously, we know that x plus y and x plus y are common sub-expressions. So, what happens is x plus y will be assigned to a new temporary variable called as u, and we will say here a is equal to u, we will say here c is equal to u. Okay. Now, at this particular point, I am not eliminating anything else, I am simply eliminating the common sub-expression only. Ultimately speaking, since a also computes x plus y and c also computes x plus y, the result of a into z and result of c into z is also going to be the same, provided between statements this and similarly between statements c and d, the value of z or a and c has basically not changed. So, this kind of like an induction based rather indirect common sub-expression is not handled by the algorithm we have just now stated. So, how do we do this? This is what we have just now said, T2 is equal to 4 into I, T3 is equal to A of T2, T6 is equal to 4 into I, T7 is equal to A of T6. Now, what did we say? Scan through the last till I get the common sub-expression 4 into I. So, compute that and use it as a temporary variable u. So, I have here u is equal to 4 into I, and then I say T2 is equal to U and T3 is equal to A of T2. So, this is what we have just now did, and similarly wherever this occurrence 4 into I is available, replace everything with T6 with U basically. Okay. Now, finally, we can get rid of this U, where I can simply use U in place of T2 or T6 or whatever it is. Okay. So, that can happen in the next step of optimization. Now, the next one is you can also implement global common sub expression as a value numbering scheme. Now, we already know what is a value numbering scheme, where you will have it as a hash table kind of scenario, where every statement will have 3 components, will be the LHS of an expression and the corresponding RHS basically. And here for example 4 into I is available at line number 15. Then what we do here is the reference of the line number is substituted for further computation of the same expression 4 into I. So, that is what is available here. As we already know A of T2, because this is also A of T2, this is also A of T6. We already know T2 and T6 are common expressions, therefore, I can replace one with the other. Therefore, here A of T2 is computed in line number 18, the same thing can be looked upon as assignment to T7. So, this is one more thing of global common sub expression elimination. Now, the next one is copy propagation. As we have seen in the earlier example, eliminating global common sub expression will result in a lot of copies getting generated. Okay. Now, our aim is to get rid of these copies because the statement does not make any sense. Okay. So, what we do here is supposing statement S has x colon equal to y, determine where the value of x is used. Okay. And substitute y in place of x, where u is a statement that uses y. So, between the statement S and between statement u, if the values of x or y hasn't changed, then what we can do is wherever x is going to be used, you can substitute in place of that x, y itself. Okay. So, in the statement S must be the only definition of x reaching u. So, this is what we should ensure, that is between statement S and statement u, the value of x or y should not basically change. Now, this information can be available or can be got from looking at the UD chain, that is use define. So, wherever somebody is who is using on what variable has been defined. So, this can basically be giving you information about whether x is going to be changed or not changed. And on every path from S to U, there are no new assignments to y. So, this can basically be looked upon as a new data flow analysis problem, where we can look at assignments, the definitions of reaching definitions of y, so that it is not going to change, that then that can basically be used as an information for identifying copy statements basically. So, let us look at this. There is one thing called as forward copy propagation. Forward propagation of RHS of an assignment or moves. So, this is basically done, and it reduces the chain of dependency, and it typically creates what is called as dead code. So, R1 is equal to R2 here, and this says R4 is equal to R1 plus 1. So, wherever R1 is used, I could replace that with R2. So, R4 is equal to R2 plus 1. Therefore, this basically becomes a redundant or a dead code. Now, the algorithm for copy propagation based on the data flow equation is out of B can be thought of as the copy generated in B union in of B minus C kill of B. So, whatever it gets killed, that is subtracted from whatever is input as a copy union whatever this basic block basically generates as a copy statement. And in of B is looked upon as the intersection of all the out of P, where P is a predecessor block, and in of B1 is null, where B1 is the first block of your control flow graph. Now, this logic here is exactly similar to the available expression algorithm computation, and so the same algorithm can basically be adopted for computing this basically. So, what we did in available expression is out of B1 is assumed to be in of B1 to start with, and then we kept on iterating till the 2 iterations basically remains as the same result. So, till that we kept on iterating. Now, this is the example here, x is equal to y is one assignment statement here, and block B2 basically defines y, and block B3 defines x. Okay. and block B4 and B5 uses X basically. So, what we have here is copy generated by B1 is X is equal to Y, generated by B3 is X is equal to Z, and what gets killed by B2 is X is equal to Y. That is, whatever was defined here, if it follows this particular path, that gets killed here, okay. And so therefore, C kill of B1 is X is equal to Z. So here, as we know, how do we define kill? Kill is whatever this particular basic block creates, that has to be subtracted from all other definitions or all other copy segments basically. So here kill of B1 is X is equal to Z, and so for all other things, C gen and C kill are null. Okay, this creates Y, and this X is available in the RHS. So here X is equal to Y is killed by X is equal to Z, and this anyway assigns a value to Y, so I cannot use this in this particular path also. So the value of Y changes here, that is, I cannot use this common expression here in this particular statement. So this example has no copy of X is equal to Y or X is equal to Z reaches B5, okay. So I cannot, this does not result in any copy statement at all. So the algorithm here is a flow graph with use defined chains and the C input of all the blocks, and DU chain that has the use of all definitions, that is also given. Output will be a revised flow graph eliminating the copy statements. So the algorithm here is, for each copy statement S, X is equal to Y, we have to do the following: determine the uses of X that are reached by this definition, determine whether for every use of X, S is in the input of B, where B is a block for this use and no definitions of X or Y occurred prior to use. So this is very important here. And if the statement meets this condition, remove S and replace all uses of X by Y. So we have to do this for every statement and for every block. So look at the UD chain basically, determine the uses of X that are reached by this particular definition, and determine whether for every use of X, S is in C in of B, where B is a block for this use and no definitions of X or Y occurs prior to this use. So X is equal to Y, I can look at is using UD chain, and whether the definition chains, the use chains based on this definition defines only this particular statement is what we have to basically check for. After this check, we can ensure that this is, I can replace wherever X is used by Y itself. Now, copy propagation typically gets created due to global common subexpression elimination. The next one is constant propagation. Constant propagation, the forward propagation of moves or assignment of the form Rx is equal to L, where L is a literal, it is a constant. So replacement of Rx with L wherever possible is a alternate. So I have something like A is equal to 1 here. So wherever A is being used, I can replace that with the value 1 itself, and the definition should be available at the point of replacement. That is, no further change should be occurring for the variable Rx. So if that is the situation, I can basically replace Rx with the literal value L itself. Now, copy propagation elimination results in unreachable code or dead code. So what we do here is, supposing I have the following basic blocks BB1, BB2, BB3, BB4 and BB5. There is a loop here, there is a loop here, and entry is on to BB1, BB4, and then that goes to BB2 and then comes to BB5. So BB3 is never getting included at all. So BB1 to BB4, back to BB2 and then to BB5. So that is a clear possibility. So BB3 is going to be a dead block. So you can eliminate that by looking at as a depth first search algorithm, where we can start visiting every block and then use a flag variable to ensure that the block is visited or not visited. So like that we can try to get rid of some unreachable code. Okay, next one is the loops. So loops, we have looked at 3 cases where you will have what is called as loop induction variable elimination, strength reduction and code motion. So the first one is loop invariant computation. So, in this example, the UD chains, the use defined chains could be used to find out values that will not change as long as control stays within the loop. So, that can basically be computed, and the loops can typically have at least one way to get back to the header from any block in the loop. So, this is one more requirement for identifying the loop invariant computation. Supposing x is equal to y plus z is at a position in the loop and all possible definitions of y and z are outside the loop, then I can consider y plus z is loop invariant. That is, within the loop y and z does not get changed, okay. But I will be in a position to compute y plus z repeatedly throughout the loop without altering y and z, means that is going to be a waste of effort and time. Therefore, you can call this expression as loop invariant. It is not dependent upon the loop. Now, the algorithm for this is a loop L consisting of a set of basic blocks having 3 address statements, and the set of 3 address statements that compute the same value each time executed from the time control enters the loop L until control leaves L will be the output. So, what we have to do basically is mark the statements whose operands are all either constants or have all reaching definitions outside L as invariant. So, you have to start by marking some statements as invariant. The condition for marking them as invariant is those variables who have all definitions reaching outside the loop or statements that has a constant involved. So, the constant is also not going to change, right. So, those statements are marked basically as invariant, and repeat the following steps until at some repetition no new statements can be marked as invariant. So, mark invariant all those statements not previously marked, all of whose operands are either constant or having definitions reaching outside L or having only one reaching definition which is marked invariant. So, here you are looking at as a indirect scenario where some statements have already been marked invariant, and you can consider new statements as invariant where their only reaching definition is already marked as invariant. They can also be considered as an invariant statement, or the simple logic itself where that statement will have all reaching definitions outside the loop here. They can also be marked as invariant. So, you keep accumulating to the list of invariant statements, and that thereby you can identify statements that are going to be loop invariant. Now, after determining loop invariant statements, the job is now to perform code motion. So, the code motion is typically applied to statements found to be loop invariant. So, first thing is you have to mark them as loop invariant. 3 steps. First step is statements that has the definitions defined outside the loop, that has the reaching definitions outside the loop are marked as invariant. Second thing is statements whose definitions will be to a point where the statements are already marked invariant is also a invariant statement, or again you can go as a repetitive job where I can say those statements which can also be already marked invariant will also be invariant. Okay. So, these 2 steps are used to find out statements which are going to be invariant statements, and after that the job is now to perform code motion. It is typically applied to statements found to be loop invariant, and typically the statements are moved to the pre-header of the loop. Okay. So, we have to move this to the pre-header of the loop, thereby the computation is going to be reduced by a lot of time, because it is going to be executed exactly only once as against the number of times the iteration basically is performed. Some conditions you have to be checked and applied to perform code motion. So, the conditions are, supposing say you have a statement x is equal to y plus z, and you have a basic block containing this statement S, and this block should basically dominate all exit nodes of the loop, that is a successor node that is not in the loop. So, this is what is the next condition. The first one is it should basically be available in a particular block, and this block should dominate all the exit nodes of the particular loop. The second constraint is no other statement in the loop should assign to x. Okay. That can be definitely found out. Yeah, we can look at y plus z is loop invariant. So, you can basically find out whether x is going to be assigned by some other variable, and no use of x in the loop is reached by any other definition of x other than this statement. So, I cannot reach this particular step using any other alternate path, I have to come through only this particular scenario. So, the algorithm will be a loop L with UD chain information and dominator information that should dominate all the nodes for exit scenario. And output will be a revised loop with a new pre-header and some statements move to the pre-header. Okay. So, what do we do here is identify the loop invariant statements defining x, and for each statement S defining x, find that it is available in the block that dominates all exits of L, this has to be verified, and that x is not defined elsewhere in L. So, you are not defining x again in the loop, and all uses in x, L of x can only be reached using the statement yes. So, the statement should be encountered that computes x, and that should be used by subsequent statements, that is what we have to find out. After doing this, move in the order found by loop variant algorithm each statement S to a newly created pre-header. So, you create a pre-header and then move these statements ensuring that the properties have been satisfied. Now, for example, here this is a case of illegal code motion. So, I am defining I is equal to 1 here, I am checking whether u less than v go to B3, okay, and if not it will come here, it will compute v is equal to v minus 1, and then it will compute j is equal to I here after this condition is basically satisfied, and then it will go back to B3. Now, an alternate path will be assigning I is equal to 2 and u is equal to u plus 1. Now, this I is equal to 2, it is an assignment statement. So, therefore, it can be identified as loop invariant because subsequent values of definition of I. Okay. So, j is equal to I is defined here. So, I cannot move this to the pre-header because only if it comes through this particular path, the value of j gets I as 2. There is no reason that it has to come through this particular path. This is also a valid path only. Therefore, in that case, j will be having a value of only 1. So, this is an illegal code motion. So, you have to ensure that you will consider all possible paths to check whether the value of a particular variable remains as it is or the way how we interpret. Okay. That is, care should be taken on that. So, to summarize this particular module, this module we have discussed algorithm for common sub-expression, which is global common sub-expression and copy propagation. We have also looked at some unreachable code and how to eliminate those unreachable code using looking at all possible loops. We have also looked at the code motion and the loop invariant computation for loops is concerned. The next module will discuss the other loop optimization techniques and further optimization that is possible with respect to what is called as dealing with aliases. Thank you.